Hi everybody, this is Jim Corkins and welcome again to your physics class. We are doing the 1.5 tutorial and this tutorial is about acceleration using vector addition and subtraction in one dimension. So the tutorial specific name is kinematic equations kinematic equations 1. So here is the tutorial. You will be given two vectors. Well, actually, not all the time you will be given two vectors. Sometimes you'll be given two vectors. Sometimes you'll be given an equation. And sometimes you'll be given a velocity versus time graph. So whatever you're given, you're supposed to figure out the other stuff from that. Okay? So in this case, we're given an initial velocity vector and an acceleration vector. We have to find the final velocity vector and displacement vector. We could use vector addition to do that. We then have to create a delta x, a position versus time curve fit, and also a velocity versus time linear fit, as well as creating a velocity versus time graph. Okay, and the graph doesn't have any specific units to it, but you have to write those out yourself. Okay. So here we go. Here we're given a velocity vector, which is pointed to the right. Looks like 6. So this is going to be positive 6. Each block represents a meter. And since this is from this is supposed to be positive 6 meters per second. And this acceleration vector, which is pointing to the left, this is going to represent negative 2 meters over the period of negative 2 meters per second change in velocity over the period of 1 second. Okay, so we know the initial velocity vector, we know the acceleration vector, and we know the period of time. Now there's a lot of ways to get the answers to this, and I want you to use whatever way you're comfortable with, but also try to stretch. So for this case, we start off with a positive 6. So I'm going to number this 1, 2, 3, 4, 5, 6. So this is going to be positive 6 up here. This is going to be then positive 4. I'm just going to count by 2's for the sake of time. And this is going to be negative 2, negative 4, and then negative 6. These are all meters per second. So our data is going to start here at the 0 second mark, and it's going and I'm going to count. So this is going to 1, 2, 3 seconds. So this is going to be 3 seconds, and 3 seconds is going to end right here. Okay, so our data starts here, and we need to figure out what the final velocity will be at the end of that. Now, you should note the equation for V final is this. It's the basic equation is A delta T plus V initial. Okay? Now we need to figure out the final velocity vector. Okay? And we're given a negative acceleration vector. Okay? So it's going to be accelerating to the left. So we know this is going to be given as a negative. So we're going to replace some of this information here. So starting with equations partially and starting with this. We know this acceleration vector is going to be a negative 2. Actually, I'm going to leave the A there. And I'm going to write out the equation in full. So this is going to be negative 2 meters per second change in velocity for every second. That's the acceleration, delta t, and plus 6 meters per second. If this vector was pointing to the left, you'd have to put like a negative 6 meters per second. So the final velocity, if we put in 3 seconds here, so 3 times negative 2 is going to be negative 6. So this is going to be negative 6 meters per second. That second will cancel out with this. Plus 6 meters per second. So the final velocity is going to be equal to 0. Okay. And so what this would look like if you did vector addition. Okay, so here is our initial velocity vector. It's going to be pointed to the right. 1, 2, 3, 4, 5, 6. So that initial velocity is equal to positive 6 meters per second. Now we're going to have 3 of these acceleration vectors, right? Because it's 3 seconds. So I'm going to take this acceleration vector and I'm going to use red. Here's one acceleration vector. Here's 2 acceleration vectors. And here's 3 acceleration vectors. Okay? And so, again, we are starting here and we're finishing right here. So that final velocity is equal to 0. Okay? So the overall final velocity vector is equal to 0. In other words, we started at positive 6 meters per second and we're ending here. So this right here is going to be our graph, and the slope of this is going to drop by 2 for each second. So down 2 and over 1, so that's 1 second, down 2 and over 2, this is the second, down 2 and over 3. So the slope of this line is going to be -2 meters per second change in velocity for every second, and that is our acceleration vector that we were given. Okay. For the displacement vector, we could use equations, but we could also work it out mathematically. This is going to be 1/2 the acceleration vector, delta t squared, plus the initial velocity, delta t. So when we put in our values, this is going to be 1/2 of -2 meters per second for every second. You know what? I should do this below here. So this is going to be 1/2 of -2 meters per second change for every second. That's the acceleration, delta t squared, plus the initial velocity, which is positive 6 meters per second, delta t. So now we're going to throw a 3 in here. So 3 seconds here and 3 seconds that we're going to square. So our delta x vector is going to be equal to, let's put some, so that's going to be 3 seconds, so that's 9 times -2 over 2, so that's going to be -9. So this is going to be -9 meters plus 6 times 3 is 18, so that's 18 meters. Didn't need to pull up a calculator. Where did I do that? So the overall displacement is going to be positive 9 meters. Okay. Another way of looking at that, so the overall displacement vector is going to be 9. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So our displacement vector is going to be equal to positive 9. Another way to do that, so you could do the displacement vector with this. You could do the displacement equation not using equations but using vectors. Okay. So let's say we have our initial velocity vector, and I think I used black. We're going to have to draw 3 of those 6 meters per second vectors. So it's going to be kind of big. So 1, 2, 3, 4, 5, 6. We're going to have to draw another group. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. So it's doing this positive 6 meters per second, positive 6 meters per second, and positive 6 meters per second. And then we have to do we have a 2 meters per second for every second divided by 2, so that's a -1 times 9. So essentially we got to take this vector and divide it. I think that should be, this is supposed to be, I'm so sorry, this is supposed to be 2. Sorry, that's supposed to be 2. Anyways, we're going to divide that by 2. So now we're going to have a -1 meter per second, and then we're going to take 9 of those. So, and you could just do one big vector pointing. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So that's going to be so this is the 1/2 times a -2 meters per second squared times 3 seconds that we're going to square. So overall that is -9. So let's just count 1, 2, 3, 4, 5, 6, 7, 8, 9. So yeah, 9 right here. And so this black one starts right here. Just want to make sure I got everything measured out. This is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oops. So I got to take off 1 here. So this is going to be the 6. Right there. I must have miscounted in this middle one. All right. Anyways, so we started right here. 1, 2, 3, 4, 5, 6. And then another 1, 2, 3, 4, 5, 6. And then another 1, 2, 3, 4, 5, 6. And then we walk to the left 9. So, which is right here. So we started here, we ended here. So this is our displacement vector. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's delta x, and that is equal to +9. So that's how you could do these problems given without just doing equations and then writing the vectors over here. You can do it just with your displacement vectors here. Okay? All right. Let's go on to another one. So here you're given an initial velocity vector, which is 2, and you're given a final velocity vector, which is 1, 2, 3, 4, 5, 6, 7, 8. So just count again. So it's 1, 2, 3, 4, 5, 6, 7, 8. Okay. So we're going to call this +8. Actually, I'm going to use blue for that. So this is going to be +8, and the initial velocity vector is going to be +2 meters per second, and this is +8 meters for every second. A lot of ways we could do this problem. We need to find the acceleration vector that has been working on this over a period of 3 seconds. And then the displacement vector we're going to have to find from there. So let's start with the graph this time. So we start out here, and let's, so we're going to count by 2s. So this is going to be 2, +2, +4, +6, and +8. And this is going to be -2, -4, -6, and -8. And this is over the period of 3 seconds. 1, 2, 3. So let's put a 3 second right here. So it starts at a +2 meters per second. And it ends at a +8 meters per second. So this graph is going to be pretty easy to do. Okay. So the slope of this line is our acceleration. So that's the slope of that line is going to be 2, 4, 6, and then over 3. So that's going to be a positive 6 meters per second. Meters per second change in velocity over the period of 3 seconds. So that is going to be a positive 2 meters per second squared. Okay? And I should have used red for all of that. I need to rewrite it anyways because my handwriting is terrible. Try it again. So that's going to be a positive 6 meters per second change over the period of 3 seconds. So that's 2, 4, 6. Yep, right. Okay, so this is going to be positive 2 meters per second squared. So the acceleration vector is just going to be a little guy, which is positive 2 meters per second squared. So writing our equations, which we don't have to solve for anything, we could just write our equations, which again is going to be a delta t plus initial velocity, which should be black. So this acceleration is going to be negative 2 meters, positive 2 meters per second squared, delta t, plus the initial velocity, which is positive 2 meters per second. Okay? All right, so in order to do this part, if you want to do it correctly and do your vectors here, we have to take our final velocity vector and subtract the initial velocity onto the other side. And then what you have is basically this is the acceleration vector right there. So if you're given we're given an initial velocity vector that is pointed to the right. Well, the negative of that velocity is going to be 2 meters per second to the left. So which is the negative initial velocity. So in other words, if we take our final velocity vector, which is 1, 2, 3, 4, 5, 6, 7, 8. So that's v final. That's equal to positive 8. And we take our initial velocity vector and subtract it from it, which is going to be right there, which is going to be negative 2 meters per second. What we're going to get is an answer which starts here and ends here, and this is the a delta t vector, right? And so this guy is a delta t, which is going to be 1, 2, 3, 4, 5, 6. So this is positive 6, and that's meters per second. Yeah. So in other words, we're going to do, so this is positive 6. So here's my point. If a delta t is equal to positive 6, and I'll do this math over here so you know what I'm talking about. A delta t is equal to positive 6, and if we take a, if we take delta t and divide it by both sides, and this is meters per second, and I should have put the units on that, per second, meters per second. Now we're going to divide this positive 6 by 2, by 3 I mean. So this is going to be positive 6 meters per second divided by 3, which is going to be positive 2 meters per second squared, right? Or positive 2 meters per second for every second, right? So that's how you could do this. And then, so in other words, this is our acceleration vector, A. So that's going to be positive 2 meters per second squared, right? Okay, for the displacement vector, every time I do this, I have to write it out. So it's going to be 1/2 the acceleration vector, and this is going to be delta t. And you know what? Let's go directly to the equation, putting our values in. 1/2 the acceleration, which is positive 2 meters per second squared, okay, times delta t squared. We're going to add to that the initial velocity, which is positive 2 meters per second delta t. So putting in 3 here, seconds here, and squaring it, and this is 3 seconds here. So in other words, we're going to get 2 meters per second and multiply it by 3. So we need the initial velocity vector, which is 1, 2, and 3. So that's the initial velocity vector plus the initial velocity vector and plus the initial velocity vector. There's 3 of those. And now we're going to add to that the acceleration vector, which is going to be 2 divided by 2, which is going to be 1 meter per second squared times 3 seconds squared, so that's going to be 9. So we're going to take this guy and we're going to add 9 to it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is right here, the 1/2 2 meters per second squared times 9 seconds squared. So overall, the displacement vector is going to start here, and it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So that should be positive 15 meters, which is the displacement. Let's see if that's true. So this is 6. So this delta x is going to be equal to, so this is going to be positive 9 meters plus 6 meters, which is going to be equal to positive 15. It works. If you don't have enough room on this, just so we'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 11, 12, 13, 14, 15. So try to estimate it as best you can. I think yours all have where you don't run off of this. You're given plenty of room to do it. So the displacement vector is going to be equal to positive 15 meters. Okay? And this is the acceleration vector. All right. And so let's make this one a little bit easier. I'm going to call this just 2 blocks to the right. So here you're given an initial velocity of positive 2 meters per second, and you're given a displacement vector which is pointed 1, 2, 3, 4, 5, 6, 7, 8, 9 vectors to the left. So that's negative 9 meters. Okay. Now, there's a lot of ways to start this one, and I'm not sure where to start, but since I have delta x and I have the initial velocity, that just tells me to start right here. So this is going to be 1/2 a, and then we're going to multiply this by, you know what, I'm going to use purple for displacement. Anyways, we're going to multiply this by, over the period of 3 seconds, so times 3 seconds, which we're going to square. And then we're going to add to that the positive 2 meters per second that we're then going to multiply by 3 seconds. Okay, so this is 1/2 a delta t squared plus initial velocity delta t. We know this has got to be equal to -9. Okay, so let's do some mathematics here. So this is going to be a divided by 2, and this is going to be times 9 seconds squared. This is going to be 6 meters, and that's going to be equal to -9. Okay, so a divided by 2, that's the acceleration vector. We're going to take this and subtract it on to the other side. So we're going to get -6. We're going to bring that over there. And then we have 9 seconds squared. So this is going to be equal to, that's going to be 15. So that's going to be -15 meters. And then divide that by 9. Wow, and then, okay, so overall, here's what the acceleration vector is going to look like. The acceleration is going to be equal to -15 meters divided by 9 seconds squared times 2. So that acceleration vector, goodness gracious, don't know what that is. So 15 divided by 9 equals, times that by 2. We'll just call that 3, but really the acceleration is 3.33 meters per second squared. Okay, which the acceleration vector, you go 1, 2, 3, and then a little bit past it. So this is going to be, and it should be pointed to the left. So this is negative because that was negative. So this will be 1, 2, 3 and a third. So the acceleration, which is negative, is going to be -3.33 meters per second squared. All right. Let's go ahead and start with this. So the initial velocity is +2. So we'll just count by 2's. So it starts there, and this is a period of 3 seconds. So this is going to drop by 3.33 for every second. So this is not going to look pretty. So this is right before the -2 here. So it's going to be just above that. So I'm going to use blue. So it starts here at +2. So here in the velocity versus time graph, we got +2 meters per second. And the acceleration is -3.33 meters per second squared times delta t. Okay, and plus 2 meters per second. So we multiply this guy by 3, right? By 3 seconds, whatever that is. That's 3 seconds. So that'll be -9.99 plus 2. And so -9.99 meters per second plus 2. So that's basically 10 plus 2 meters per second is going to be equal to 12. -12 meters per second. Nope, nope, that's going to be -8, sorry. Negative 9.99 plus 2 is, you don't add, so it's -8 meters per second. Okay, so if we started here at positive, so this +2, this is -2, this is -4, this is -6, and this is -8. So we're going to start here at +2. We're going to end here at -8. So right there. And so our graph is going to look like this. And the slope of that line is going to go down, where the slope of that line is -3.33 meters per second change for every second. And so since you have 3 seconds, that'll be basically that'll be a -8 will be the end. Okay. So we could just go right to here and just draw that velocity vector as 1, 2, 3, 4, 5. So starting here, 1, 2, 3, 4, 5, 6, 7, 8. So ending here. So this is your final velocity vector, which is -8 meters per second. Okay. Again, I'm going to demonstrate what you're supposed to do if you want to use the vector addition part. So this, so let's do the final velocity. Okay, so we have a +2 meters per second, which is going to go to the right, +2 meters per second. And I should start further out. So +2 meters per second. And then we are going to go to the left. So this is going to be the A delta t. So we're going to add that to the A delta t, which is 3 1/3 plus 3 1/3 plus 3 1/3. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the A delta t vector, which is equal to -10 meters per second. In other words, you started here and you ended right here. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8. So the final velocity is equal to -8 meters per second. So there's a lot of ways to do this. Again, use whatever you're comfortable with, but do try and do the vector addition and work with the equations by using the vectors like I did here and like I did over here. Okay. There's one last one to do, and this is what to do when they actually give you the velocity in meters per second. So they give you a velocity graph, which has a lot of information. It's not very hard to do. So you can mark this up. So it looks like it starts off with an initial velocity of 0. So 0 meters per second, and the initial velocity is 0 meters per second. And you're supposed to, anything red you're supposed to complete. And the final velocity looks like it's going to be +4. So 1, 2, 3, 4. So this is going to be final velocity, which is equal to +4 meters per second. Okay. The slope of this line, so this is delta t. To find the acceleration, we can just get the slope. This is going to be 4 divided by 3. So the acceleration is going to be +4 meters per second divided by 3 seconds. This is going to be another fraction. I think yours work out to be whole numbers, but 4 divided by 3 equals 1 1/3. Okay, so this is going to be, so that acceleration is going to be positive 1.33 meters per second squared. And then we could just pop this up into the equations, right? Meters per second squared, delta t, which we'll just, so that's squared, so we'll put in a 3 seconds here. Looks like it's 3 seconds from the graph, at least. And then we're going to add to that 0 meters per second times 3 seconds, which is delta t, which we didn't have to do. So you have 0 meters per second, and then we have to add to that 0 meters per second for 3 seconds is just 0. So the initial velocity is just a dot. Now we're going to add to that the acceleration vector, which is going to be 1.33 meters per second times 9 divided by 2. 1.33 times 9 equals, divided by 2, which is basically 6. So the acceleration delta t vector, which is going to be 1, 2, 3, 4, 5, 6, that is 1/2 the acceleration times 3 seconds that you're going to square. And so since you have 0 plus this, that means our displacement vector is just going to be this whole thing. You start it here, you end it here. So the displacement vector is just equal to positive 6. So the displacement is 1, 2, 3, 4, 5, 6. And the acceleration is going to be 1.33. That looks terrible. 1.33. That looks even worse now. It's like that time I tried to cook something from scratch from watching a TV show, cooking show. Went to the store, bought $400 in ingredients. When I pulled it out of the oven, I'm pretty sure it was sentient. It started talking to me. Okay, anyways. So this is going to be 1 1/3. So this acceleration vector is going to be the right positive 1.33 meters per second squared. Okay. Incidentally, for the final velocity, if we wanted to do the final velocity vector, we're going to take the acceleration vector, which is 1.33 times 3 seconds. So that's going to be 1.33 times 3 seconds, which is just going to be oh, no. 1.33 times 3. So 3.99, right? Since we already know it, but we're going to, so for the final velocity vector, we have 0 meters per second, which is this. And then we're going to add to that the acceleration delta t, which is 1, 2, 3, 4. So this is the acceleration times 3 seconds. So for the final velocity vector, if we started here, we ended here, this is the final velocity vector, which we already knew. But just making sure we could do it that way. There's a lot of ways to do these things. Okay. Anyways, that is the tutorial and I did a lot more than I should have, but I just wanted you to get a whole view of the tutorial. Yours is very much like mine, and they're quite easy. So try it out. The requirement is to complete all the red areas. So for example, in this first one, complete these two red vectors. I'm sorry, all red areas. You're supposed to complete the two parts here, write the two equations, and complete this velocity versus time graph. You're supposed to do that for each one of these until you get to right here, where you're supposed to complete all the red parts and create your equations. And here you're given an equation, you're supposed to complete all these red parts and the velocity versus time graph. And this last one is complete all the red areas for the vectors and the velocity versus time graph given this equation. So there's a lot of good variants. By the time you get done with this, you will be really good. Your knowledge or conceptual understanding of kinematics will be excellent. Okay? Please have a good day.